Good afternoon, everyone. My name is Robert Avalos,
I'm Eulalia. Udok Choi. I'm Matthew.
and this is the turbocharger gas turbine project.
Go ahead.
Okay. Just a quick run through for our table of contents. We're going to go over our objectives, functions, constraints, kind of a design methodology that we went through, system schematics, Brayton cycle needed for calculations for this project as well, conceptual design, our final design, our fabrication of the design, assembly, budget, Gantt chart, lessons learned, conclusion, and acknowledgements. Just kind of a run through of everything that we went through this project and kind of explain it to y'all.
Okay, gas turbines are a type of continuous flow internal combustion engine that follows the Brayton cycle for their operation. They are commonly used to power pumps, aircrafts, gas compressors, and electrical generators. They mostly consist of four primary components: air compressors, the combustion chamber at the turbine, and the exhaust. Our objective was to design a gas turbine capable of producing 100-pound force of thrust, or as much thrust as we can get out of our design. We needed to calculate the heat transfer and thermodynamics necessary for the design within parameters of the Brayton cycle. We need to design and manufacture a combustion chamber, oil lubrication, cooling, ignition, and fuel injection systems. We wanted to use kerosene as a fuel source, and we wanted to use a turbocharger as our turbine and compressor. Okay, the operation of our design depends on several important factors working together smoothly. Our compressor must efficiently compress incoming air to the right pressure for combustion. Our combustion chamber, the design is crucial to mix air and fuel effectively and to maintain a steady flame for consistent energy release. And after combustion, the expanded gases are vital in driving the turbine. The whole process is closely connected to the design of the nozzle, which turns the remaining energy of the gas into thrust, which drives our drives the design. It's important to have good systems for lubrication and cooling, and all these tasks make up the foundation of a gas turbine that works well and is dependable.
As far as our constraints, the first thing that we wanted to make sure was we're not going over budget. Our budget was going to be $1,000 at this point that we were thinking of. As far as that goes, we stayed below that for now. It's still continuing as well. Strict adherence to industrial safety standards, of course, making sure that we are staying within code, not doing anything out of code that's going to not only harm us, but maybe harm the project in any sort of way. Prudent selection of materials, of course, making sure that we're using things that are compatible with what we're trying to accomplish here at the end goal. Lastly, the engine design, just having dedicated focus and mitigating environmental impact like emissions and noise levels. Just some of the things that we kind of went out for constraints. As far as the design methodology, we decided to run off of a turbojet engine style. So as you can see here, it would have a air inlet, your intake, compression, combustion chamber, and then your exhaust, which would create your thrust. Parts of improvement for us would be the air intake, making sure that we had intake to supply enough air to compress within the compressor into a small space, which would then create pressure for the system. Combustion chamber as well. Combustion chamber was necessary to mix the air and the fuel, and making sure that it was systematic enough to create the thrust needed for that 100 pounds of thrust or 1 horsepower, or whatever we could exceed at this point. Again, hot gases will be blowing through the turbines, which will then create the thrust that we needed to propel. We decided to use the turbo, being that the turbo had the compressor and the turbine. After some research, we did end up deciding to choose with this turbo with a faculty advisor, and this is what we ended up kind of running with for the meantime. Here's the Brayton cycle.
So
to design the combustion chamber and safely produce the thrust, it is important to understand and study the breathing cycle. So this is the ideal breathing cycle, and the air goes into the compressor and compressed to the higher temperature and pressure. And this process is isentropic, meaning there's no heat exchange. And in the combustion chamber, the fuel is added and burned with the pressurized air. And in this process, the pressure remains constant. And then the high temperature and pressure gases expand through the turbine and produce thrust. And this schematic shows how the general gas turbine works. And this is our turbocharger specification. It has a maximum PS boost pressure of 19 psi, and all the dimensions for compressor and turbines are here. So based on this specification, we calculate the temperature and pressure for each state of the breathing cycle. This is the ideal breathing cycle calculation. We calculate the temperature and pressure for each state. And from 1 to 2, the volume decreases due to the compression and the fuel added, and it expands through the turbine and produce thrust. We also calculate the work done by the cycle, which is 190 kilojoule per kilogram, and also the efficiency, 21%. But this is the ideal case, but in the actual case, we will have less efficiency due to the pressure loss in the combustion chamber, and also the efficiency of the compressor and turbine. So with these graphs, we can assume the isentropic efficiency of compressor and turbine. So for the compressor, it's from 72% to 78%, and for the turbine, it's from 70% to 90%. So for the calculation, we used 75% for the compressor and 80% for the turbine. And these red areas are our design point, but at least we want to stay in this area, right side of the surge line. So this is our actual breathing cycle calculation. We have a higher temperature for state 2 and 4, and also lower efficiency and work done, which is 13% and 110 kilojoule per kilogram. And the breathing cycle calculation is for the general gas turbine. And after we decided to use the turbocharger, we used the JetSpecs designer for the turbo analysis. So this is a JetSpec designer program. This program is designed for turbo analysis based turbocharger based engine. So we put the compressor outlet diameter, inducer diameter, and hub diameter as an input, and we got the values for maximum RPM, mass flow rate, and temperature and pressure ratio. Even though we got a little bit lower efficiency for compressor and turbine, we still got the same value for pressure ratio, which is 2.3. And we got our mass flow is about 0.7. So if we go back to the graph, with the pressure ratio of 2.3 and mass flow rate of 0.7, we're in that blue area, which is in our desired range. And also we got the temperature for the turbine, which is 641 degrees Celsius. Our turbine housing has a temperature resistance up to 700 degrees Celsius. And for the turbine blade, it can handle up to 900 Celsius. So we're in the safe range. So based on these calculations and data, we designed our gas turbine.
So this is our conceptual design. It was primarily made just to understand what exactly we were trying to create here. So it's mainly just a model. We wanted to like kind of see how this system works and want to get a basic understanding. And then this is our final design. after finding all the specifications for our combustion housing and flame tube, this design was made. So this is our final design, and it is to scale. The way that we figured out how to make the flame tube, which is inside the combustion housing, we use the JetSpecs program as well for that. Basically, you just put in your inducer diameter from your turbo, which is the compressor side inlet, and then you have it calculate the rest of the stuff as well. You select your drill hole diameters. In our case, we chose a 1/4 inch, 1/2 an inch for our secondary, and 1 inch for our tertiary. And then it pops up all of your diameters. So our flame tube length ended up being 1 foot, and the diameter used came out to be 5 inches. And then here are our fabrication plans that I handed off to our fabricator slash welder. The left is our housing, which you can see on the outside. And then the right is our flame tube, which is inside the housing. And then here's a couple of pictures of our fabrication process. On the left side, you'll see all of our metal sheet pieces that were cut. We couldn't find big enough pipe for this project, so we had to actually have it cut into pieces, as you can see in the left picture, and then we had to have it rolled, or else it was going to be very weird sizing of our parts. And then our middle picture is the housing welded together, and on the right of the housing is our flame tube. And then on the right picture, that's my dad welding. He welded a project for us. So this is our flame tube. Like I mentioned before, we use the JetSpecs program to find the specific diameters or specific dimensions. Our metal sheets were laser cut by Ryobi Metal in Houston. They were rolled by Sammy Campo and Campo Sheet Metal Works in Houston as well. And then, as I said, all the parts were TIG welded by Eulalia Martinez Sr., which is my dad. The material used for this part, for the flame tube, was carbon steel sheet, 10 gauge. And as far as the combustion chamber, after finding our specific dimensions of the flame tube, we designed this part around the flame tube. This part is obviously necessary to hold the flame tube in place, as well as the combustion. The parts or the material that was used for this part was carbon steel sheet as well, and 3/16 stainless steel, which is for the piping, the smaller piping. And then here's a picture of it assembled. You can see the compressor, rubber coupling, how the air flows, as well as our combustion chamber, and the turbine side is on the back side.
And then going over our parts list, everything that we acquired from the turbocharger to kerosene, our total cost ended up being around $950. This is what we have for now. There's still some extra parts that we haven't acquired just yet, being that when we tried putting together, there were a few pieces that just didn't work the way we wanted it to, especially the parts that we ordered online. Unfortunately, that's just kind of how things roll sometimes. Everything else that we put together in the meantime is what we have here. We look forward to continuing as well and trying to get this running very soon. We're just there. It's just like little setbacks that are kind of holding us back right now in the meantime. And then as far as our Gantt chart goes, we did make everything to spec as far as timing. We hit everything as far as, what we wanted to accomplish in the time being that we had. We did have a little minor setback in the beginning of this project, being that we were deciding if we wanted to run with a steam turbine or if we wanted to roll on the gas side of it. We ended up choosing the gas, of course, and that kind of held us back just slightly. But as we're at now, we can't complain. This is something that we worked really hard for, and we're glad that we have something to present to y'all today. As far as lessons learned, again, product material selection, making sure that things that we ordered come in exactly the way that it's specified. Time management, making sure that we do things under a specified time period, getting everything ready and having everything essentially ready to go. Fabrication plans and drawings, again, you know, that's something simple, making sure that everything's to spec, making sure that what we give, you know, our welder or fabricator, make sure that he knows exactly what he needs to do and making sure that what we get is what we want. Again, project focus, project selection, like I was saying before, whether we're deciding to do the gas or we're gonna do the steam, we end up choosing the gas, but having a pure focus in the beginning, making sure that you know what you want to do before you start it is essential, of course. And then SolidWorks, we really want to show you all SolidWorks simulation of this running. Unfortunately, SolidWorks would not accept the project that we had threw in there as far as the flow went. It just, for some reason, it did not want to be compatible with it. That's something we're still messing with as well, trying to see if we can get something going there. But as of right now, we do not have a SolidWorks simulation for you. Conclusion. We just want to finish the assembly. I mean, we're right there. We're on the cusp of it right now. As you can see, we have essentially the meat of it is just getting little parts put together from now. Then we want to test, analyze, you know, make sure that everything that we have calculated is up to spec and that it does what it's intended to do. Again, just refine design and achieve desired results, which would be 100 pounds of thrust, or at least moving this cart is the goal of that, is creating thrust enough to move that cart. Again, we'd also like to just give our acknowledgments. Thank you to Texas A&M Kingsville for the education that they have provided for us. Again, thank you, Dr. Grady or Professor Grady, for helping us out as well. For senior design, he's also one of our mentors, and Dr. Sangsuli as well. Ryobi Metalworks in Houston, they were great help with this. They fabricated everything for us for the most part, as well as Eulalio's dad was doing the welding for us. Again, thank you again to Texas A&M Kingsville for everything they've done for us as well. Any questions?
Looks like we'll have about 10 minutes, maybe even 11 minutes for questions since you guys are the last ones. So judges?
So I work in the oil and gas side, so we work a lot with compressor units. And one of the challenges that we run into is vibration. So whenever you guys get it going, we'd be interested to see how much vibration this creates. You know, like I said, we work in bigger units. So some of the challenges when you have vibration, your connections start moving around and then they get, so it will be interesting to see how you guys can get this going.
Yeah.
How much vibration might create.
Yeah.
But something to look, you know.
To think about, yeah, for sure.
Yes, sir.
Any other questions?
You go back to what your objective was of the project.
Yes, sir.
What, from your perspective, when I listened to your presentation, I heard that you were using this to understand how turbines and so forth worked, which I assume do I have that correct?
Yes, sir. Oh, but we kind of have the concept down now. Is that kind of what you're asking?
Like you accomplished part of that,
Yes, sir.
but we don't know about the turbine. My first reaction, strongest reaction is if you really got the turbocharger for $81, you either have a heck of a purchasing agent, or you need to build a shield around it.
Yeah.
Yeah.
So
I'm an automotive kind of guy and deal in turbochargers, and man, I've looked close at an $81 turbo.
Yeah, that is something that we could kind of keep an eye on to make sure that it's not going to be, you know, like you're saying, something that might kind of blow back at us or give us a wrongful output essentially. But hopefully that's something we can do within this week is what we're shooting for. So we'll see. But we will keep that in mind for sure. We'll be extra careful with that.
The fire tube and the hole selection, what's the why behind that? I know we plugged it into a program, but do you know why it chose those holes, or did y'all choose those holes, or how does that work?
Are you speaking in terms of the whole size or,
Well,
so the
what
whole,
determined that layout and those sizes?
so the sizes are really completely up to you. There is kind of a rule when selecting them. So say like your primary holes, say they're like an inch. So then your next ones are supposed to be a quarter inch bigger than your primary. And then your tertiary is supposed to be half an inch bigger than your secondary. So that's really the only rule that we follow as far as putting them on
So like a rule of thumb or?
kind of, yeah.
So we don't fully understand the why, we just know that they're supposed to incrementally step up.
Yes.
I don't know either, that's why I'm asking. That's pretty, hey, that's kind of cool. What's the city process? So if you change it, how would it affect it?
So it's for your mixture of air and fuel. So if you make if you make them too big or add too many holes, it messes up your combustion. Meaning like you'll run too rich or you'll run too lean. So
So then is the selection process, does that align with the fuel that you're using? And I forgot what fuel you're using.
Kerosene.
Kerosene.
well, we haven't been able to test, but we watched a lot of videos and we read a lot of articles, made sure we actually understand this. So
Every reference kind of leaned towards this design style with the kerosene, essentially, is what they're saying. So that's kind of what we chose the kerosene to kind of build this plane to.
Got a question if the other judges don't. So we got a physical model here. And I'm not a turbocharger guy, so could you point out what's your air intake and where your heated exhaust goes out? Physically go there, come on.
Oh,
You can
sure.
touch it.
So let me turn it towards you.
You can just point it to
Oh,
there.
well, it's on this side, so this is your air intake. I
Okay,
just have it capped because I don't want anything to fly in there.
okay, where's your,
Air intake, and then this is your exhaust.
okay, so I thought the big chamber right there, that would be that.
The chamber is for
flow.
combustion.
Okay, so that's your combustion chamber, but if this is for thrust, wouldn't your nozzle going out, wouldn't that be important?
So your air goes through here,
No, I'm talking about your exit.
but
With
your
that
air goes through
nozzle.
here. And it combusts in here, but simultaneously air is still being pushed through here, which is gonna spin this.
But yes, but
And drive the shaft in here
But-
for your turbo.
talk about your nozzle, your output nozzle, if you're trying to get thrust. Isn't the shape of your nozzle, if you're trying to get thrust, isn't that an important part of that?
I've seen people make an exhaust and I've seen people run them without an exhaust.
Okay, so your fixture is your combustion chamber, is it attached to your,
To the car?
yes?
Yes.
Yes.
So aren't you concerned about that really hot thing right there next to your sheet metal cart?
That could raise concern. But
Where's
we
your-
did at least try to reinforce it with another steel sheet on the bottom.
Well, might need some insulation there too. So your fuel comes from the side right there.
It's gonna come
It's
from
gonna
the
sit
bottom.
underneath.
Yeah, your fuel, and then the black holes takes
This is
it.
your oil.
Okay, so where's your fuel coming?
It's gonna come in the bottom.
Okay, you might evaluate some safety concerns there.
Yes, sir.
But probably.
Again, it comes with, getting it to run first and, practice
Well,
and failure.
The first thing, we don't want to kill you guys.
Oh,
right?
yeah, no, of course,
So
that's
I'd say
the
safety is
main concern.
a little
Yeah.
higher priority than. I think we had some other questions. Go ahead.
Was there any thought process behind the angle of approach the air has as it goes into the combustion chamber? Like, did you offset it so that it kind of creates a vortex?
Yes, that's actually a really good question. So, another rule of thumb with these is you're supposed to have it above half of the plane sheet in order to create like a vortex inside.
And did you offset it from the center of the combustion chamber like this?
Yeah.
Okay.
Any other questions?
Go ahead.
So theoretically, if this thing does work, how exactly are you gonna ignite it?
So there are multiple methods. We were gonna use a spark plug.
Where would you put this?
It would also be at the bottom next to the fuel. Or there's other methods, shown, they put it right here. Somewhere along the combustion chamber housing.
You know which one would be better?
Not exactly. I mean, I've kind of seen a lot of people would put it on the end cap of the flame tube. Or I mean, on the bottom, you know?
Is there an engineering analysis tool which would allow you to evaluate that? Or
Like, what do you mean?
is it a seat of the pants kind of thing or? How would,
Do you have a baseline that you can try to use, or are you just?
Like a
gonna experiment?
simulation or?
Are you just gonna try different things and see which works best, or do you have some kind of methodology for determining where you're starting?
Well, I think from most of our references, we were gonna shoot through the bottom half because that's simply what they kind of did. From most of the videos that we watched, or people that had already done it before, they had tested, doing two different methods, and that was kind of their method was through the bottom half of it. So that's what we were using first. If that didn't work, then the process of putting it through the side was going to be our next attempt at it. But if for design methodology, like you're saying, that would kind of be our reference for that. We wouldn't have one for you now, but that would be our reference.
You guys are a second semester team, right?
Yes, sir.
Other questions? I thought I had somebody else. Go ahead.
I was gonna ask, since you're doing one of these bolts testing, to make sure they will actually suffice, like durability wise, strength wise, because I know that, the welds are very important to hold, like what's going on in there, and if something fails, that shock it.
That's
Yeah.
a good question.
I wouldn't really know exactly how to answer your question, but I can tell you that the welder is very professional and has been welding for a long time. So it's not just, we didn't weld it. It's not just some random person who welded it.
Yeah, it's not like a backyard job weld. It's professionally done welded. So until we test it, like you're saying, we won't know if they'll fail or not. But for the most part, we're pretty certain that they'll meet par that we want. Again, that's something we could throw into SolidWorks and maybe simulate. But again, like we were saying, SolidWorks wasn't working for us.
Go ahead.
Is there anything else you could include other than SolidWorks to get a simulation?
Probably like ANSYS, but I've just never used that program. So I just kind of stuck to SolidWorks as SolidWorks is kind of my favorite program to use. So I just trying to get that to work. As far as other programs, I probably like ANSYS is what I've heard, but I don't know how to run that. I don't have that either. So
Also being on time constraint and trying to get everything ready for this.
Clarify, so there hasn't been any analysis done on the welding or the material for your combustion chamber. And so I think you said you're gonna run it and test it and hope it doesn't explode.
Well, and yes and no. Like he said, that was a great question, right? We could still throw it into SolidWorks with the welds and see if it'll hold under some kind of pressure, at least, right? Again, we could, like I said earlier, we could test it and see if it's gonna hold, but that wouldn't be the right way to go about it. I agree with that. Yeah, I do agree with that. But again, like you're saying, the welds are done, we're done professionally, so I do trust these welds. I don't expect it to break, but if it does, that's something that we should look into as well.
We built a carbon fiber drive shaft and we threw it under a car and I still hid when he cranked up the car. I'm not gonna lie.
I helped with the simulation. I knew it was fine.
The glue was good. Good glue, yes.
Now it's been dropped and thrown around and used for other stuff. I wouldn't put it on a car now.
I'd like to have a video of this thing moving when you get it done.
Yes, sir.
Yeah, you guys have somewhere where, cause I wanna see it too.
Like a page, essentially.
Yeah,
well, we did have to set up a page for class, so we do have a page that's gonna be in our report.
Will you send us a link? The judges a link?
Yeah, really great. And if I get it, I can send it. Well, we'll get somebody to. Other questions for them? So let's give them a big hand.